Okay, thank you very much for the introduction. Yeah, my name is Max Ramgraber. I'm an assistant professor at TU Delft, and this is work that's done in collaboration with my colleague Berent Lunde from Equinor. And we'll talk about triangular measure transport filters and smoothers and how we can make them adaptive in scale for very high dimensional problems. So to begin, let's motivate the study a little bit by looking at the data assimilation problem, where we generally have some kind of joint distribution between states we're interested in and quantities that we can observe or measure. And if we collect data in the real field, then this data basically constitutes a hyperplane in this joint space, shown here in this gray vertical bar. And then ensemble data assimilation methods usually try to transform our prior ensemble into posterior samples. The ENKF, of course, does this with a very sample-efficient linear transformation that basically takes this ensemble and projects it linearly onto this hyperplane, yielding the posterior samples shown here in the histogram on the right side. And this is very close to the real posterior if our joint distribution is multivariate Gaussian. Unfortunately, that's not always the case. If our dynamics are nonlinear, or our prior is non-Gaussian, or our noise is non-Gaussian, then our joint distribution might exhibit some non-Gaussian features. And if we're very unlucky, it might look something like this. This is, of course, a completely made-up distribution, but it highlights some of the limitations of the ENKF quite nicely. So here, if we were to condition this joint distribution on the value indicated here by this gray vertical bar, we would expect to get some kind of trimodal posterior because we're slicing this in 3 different locations. But if we naively apply the ensemble Kalman filter, that's not the posterior samples we're getting, because there's just no way that a linear transformation comprised of these straight and parallel lines can turn this prior into something that's trimodal. For this kind of distribution, we need a more powerful update, and we need nonlinear updates. Now, there's of course a lot of different methods we can use to do so: particle filters, Stein variation, gradient descent, and so on. But in this presentation, I want to focus on triangular measure transport, which I think is a quite promising way to do nonlinear data assimilation, in particular because it uses the same update strategy as the ensemble Kalman filter. It also transforms the ensemble, but it allows the update to be nonlinear, which looks a little bit like this, where we still project our samples, but now we can do so in a nonlinear way, which can retrieve, in this case, for instance, the correct trimodal posterior. And of course, this also works for other distributions. So how does this method work, and how can be applied to real complicated systems? So the key idea here basically is that if we want to get the posterior of a complicated joint distribution, it helps to know what the joint distribution or the target distribution actually looks like. So here it's clearly some kind of spiral. And transport methods basically try to learn this underlying distribution from the ensemble by trying to transform it to a simpler distribution, a reference distribution, often a standard Gaussian. And if we make sure that this transformation is invertible, it can not only transform our ensemble to standard Gaussian samples, but it can also transform standard Gaussian samples back into approximate samples from our simulator. And the same idea also underlies a lot of generative modeling techniques like normalizing flows, for instance. What makes transport methods, triangular transport methods, special is that we posit a certain structure for our triangular transport map. Specifically, our transformation, our map, should look a little bit like this, where the full map is a vector of transformations, so-called map component functions, each of which transform one variable in our system, and each of which depends on progressively more variables. So the first map component function depends only on x1, the second one depends on x1 and x2, and so on until the last map component function depends on everything. And to make sure this entire structure also remains invertible, we can further require that every map component function must be monotone in its last argument. So for instance, the third map component function S3 would have to be monotone in x3. Now, this structure has a number of really interesting properties. Chief among them is the ability that we cannot just sample the joint distribution, but also conditionals of the joint distribution, which again is very relevant for data assimilation where we are interested in posterior samples. One problem with this approach is that if we apply it naively, this scales very poorly with dimensions. In many systems that we care about, we might have hundreds of thousands, if not millions, of states in our data assimilation problem. And since a triangular map needs one of these functions for each variable, we need 1 million of these functions, and they also get progressively more expensive. So the last one would depend on 1 million arguments, which becomes computationally infeasible. We're basically scaling exponentially with dimensions. So this is a huge problem. But fortunately, transport methods also have some tricks that allow us to alleviate this problem. And key among these tricks is the ability that maps have to exploit conditional independence in a very clever way. So to set this up, consider that whenever you have some kind of joint distribution, you can always factorize this in this kind of triangular way over here, split it up into this product of marginal conditionals. And as it turns out, this factorization has a very close correspondence to the triangular map, where basically the inverse of every map component function samples one of the terms in this factorization. So this becomes a little bit more clearer if we adopt the view of maybe a graphical model, where we can see that this first map component function basically just samples or gives us this node. The second map component function gives us the next node and the edge to the first one. The third map component function gives us the third node and the edge to the previous ones, and so on. So we can see that a full triangular map that scales poorly corresponds to a dense graph. Now, dense graphs can be useful because they basically account for every direct statistical dependence that could possibly exist in our distribution. But in the finite sample size setting, in which we're always in data assimilation, this can become a problem because it exposes us to a massive risk of spurious correlations, and then localization has to come in to fix this problem. But fortunately, in many settings, we don't need a dense graph. In many settings, we have a lot of conditional independence properties that allow us to remove some edges in this graph. And likewise, exploiting these properties allows us to remove some dependencies from the terms in the factorization and also from these map component functions. And that actually turns out to be an extremely useful property, because not only is it a very sort of powerful form of localization, we can basically build our localization directly into our update, but it also makes the maps significantly more computationally efficient, because these map component functions here now, instead of depending on 4 arguments, it now only depends on 2. And that makes it cheaper to evaluate and cheaper to optimize. And if we have enough conditional independence properties, which in gridded systems we often have, then this horrible map might actually suddenly become something that only scales linearly in computational complexity with the dimensions of a system. So if we have enough conditional independence properties and we know how to exploit them, then these methods can theoretically scale to almost any dimension we want. This, of course, raises a question: how do we find these conditional independence properties in whatever gridded system we might have? And there's a lot of strategies we could use to find these. The one that we're using in this work is an algorithm that was proposed by Florian Schäfer in 2021 for sparse Cholesky factorization in systems where you have spatially distributed samples. The idea is basically that you begin with an empty set, and then you select the cell or the state that's farthest away from the boundary or from previous entries in your set. The set initially is empty, so we just consider the boundary for now. And then you try to figure out the radius of the cell you've selected to either the boundaries or the next entry in the set. So initially, this is just the radius here. And the radius is initially twice as large as the domain, so it's somewhere out here. So everything is in the radius. And then we try to find if any sets, any states or cells in the set are within twice this radius. And if they are, we assume that this cell we've selected depends on the previously selected state. Once we've done this, we add the cell we've selected to the set and repeat this for the next cell in our grid, which now again tries to maximize the distance to previous cells and to the boundaries. So for example, it might be here, the radius now has shrunk. And since this previous cell is in the twice the radius, we now say this cell depends on that one. So we build an edge between them. And if we keep doing this, this algorithm eventually finds cells that no longer depend on everything we've treated so far. So for example, here, these 2 cells are outside of our range. And ultimately, this basically fills in the grid with a strategy that looks like this. So a full dense triangular map would be completely gray here in the lower triangular part. But we see here it's actually mostly white. So if we follow the strategy, we get extremely sparse maps that really only scale linearly with dimension. And we will see how that performs in a numerical example in a little bit. But before we go there, I want to go to the second part of this presentation, because in triangular maps, it's not only about how you scale to high dimensions, but also how you avoid overfitting. The maps that we're using are parameterized. And if you add too many degrees of freedoms to your map, you might actually risk overfitting, which again incurs bad bias variance trade-offs and hence decreases the performance of your filter. So to understand how we can avoid that, let's first take a look at what these map component functions actually look like. So we're actually quite free to define these map component functions however we want. Some people use neural networks for them. But a very efficient way to define them is just to turn them into basically sums of basis functions, where each of these basis functions depends only on one of the arguments of this map component function. Here I've grouped all basis functions that depend on the same argument into sort of vectors. And you see that this last part here again has to be special because we might recall from earlier, map component functions must be monotone in their last argument. And that's, for example, something we can achieve by making these basis functions monotone and keeping their coefficients positive. This still leaves us with a lot of freedom for what basis functions we can choose. So we could choose polynomials or radial basis functions. And we are now specifically making use of P-splines. So if you've never heard of P-splines, they are basically penalized basis splines. Basis splines look a little bit like this. But the penalty part comes in because we are penalizing second-order differences between the coefficients at neighboring knots, at neighboring splines. So this basically causes the splines to only grow or decay in a smooth way, which results in a relatively smooth function that comes out of there. And this has actually a number of really interesting practical advantages for avoiding overfitting. The first one is, of course, the penalty term promotes smoothness, which makes our maps perform a little bit more robustly. And secondly, it also controls the degrees of freedom in our update, or the degree of nonlinearity. So if we enforce the second order difference very, very strongly, then our P-spline map actually becomes linear. And if we don't enforce smoothness at all, then we can adjust each of these basis splines independently, and we have a very, very nonlinear map. So by controlling the smoothing penalty, we can basically figure out how nonlinear our map will be. And what we are doing is that we are solving an auto-optimization problem that tries to optimize the Akaike information criterion to find this optimal smoothing penalty. This essentially would look something like this, where you see here on the left side a one-dimensional map component function. Here's our target distribution in 1D, so it's clearly something bimodal. And in black here, you see the triangular map in 1D, and here you see the output, which should be standard Gaussian. So we see that if the smoothing penalty is low, the map can be very nonlinear, and the outcome is very close to Gaussian. But as we increase the smoothing penalty, the map has to become more and more linear, and the outcome, consequently, no longer is really standard Gaussian. And you see that reflected here in the map optimization objective in gray, which is low when the nonlinearity is high, but becomes quite high when the map becomes more linear and fails to turn this into something Gaussian. At the same time, however, the degrees of freedom decrease. So the smoother we make the function, the closer we get to linear, to 2 degrees of freedom. And you see the Akaike information criterion here in blue finds an optimal compromise somewhere here in the middle, where the map is still complicated enough to turn this into something Gaussian, but at the same time also uses only as many degrees of freedoms as it really needs. So with this, let's take a look at some numerical results to see this algorithm in action. The first result I want to look at is Lorentz 63, which is, of course, very low dimensional, but very, very nonlinear. So it's a good test case to see to test nonlinear data assimilation. The first results we're considering are from a previous study where we actually manually tested different levels of map complexity. And we used L2 regularization to avoid overfitting. So this is before P-splines. Here we see that a map that only uses linear map component functions. And you can actually show that this corresponds to the ensemble-Kalman filter. So we see that as we increase the ensemble size, the filtering performance doesn't really improve anymore because we have reached the limit of what linear maps can achieve. But if we make our map component functions nonlinear by adding basis functions, say polynomials up to order 3 or up to order 5, we see that we can get substantial improvements in terms of RMSE if we have the ensemble size who supports this complexity. Now, as a comparison, if we use the T-spline ATF, which automatically tunes itself, we actually get substantially better performance with no manual tuning. And our goal, of course, is to have an algorithm where you just have to press a button and it automatically finds its optimal level of complexity. So this is quite promising for now. But of course, the setting here is relatively low dimensional. So we also considered a more high dimensional setting. So we had a very simple groundwater model, a grid size 51 by 51, so 2,600 unknowns in total. And we had an ensemble size of only 100. So our prior basically is this very bimodal conductivity field here. And we have a pressure boundary of 10 over here and 5 over here. And then depending on the hydraulic conductivities, the groundwater field spreads out accordingly. And we observe hydraulic heads at these 6 locations. So these results are very fresh. They just finished this morning. We see that here's the true field again. And this is our mean prior field and our standard deviation of our prior. And we see, of course, the prior field initially is quite uniform, and uncertainties are largest away from the boundaries. This is the result you get with an ensemble Kalman's mover. So it's actually quite close to the true field in the mean, but there are some odd things. For example, that the maximum and minimum values of the mean field are a little bit outside of the physical range that the model can produce, issues we've also seen earlier. And for comparison, here's the result we get from our triangular transport filter. So it also yields a very similar result, but it actually stays closer to the physical ranges. And if you compare the root mean square error of our ensemble with the true field, we get a slightly better performance. Of course, this isn't as exciting as Lorentz 63 because pressure fields tend to be quite Gaussian. But in the next steps, we hope to test this for parameter estimation or for concentrations, which might be more non-Gaussian. And with this, I want to thank you for your attention.
Thank you, Max. Great presentation. I am opening the Yo pod, and it seems that there are still questions that are piling up. But for now, maybe I can ask you a question. You talked about the Florent-Scheffer's algorithm for selecting the conditional independence components. And I was wondering if you can you talk about a little bit about the intuition behind it, and if you visually checked if you compare different components, you can actually see in histograms that they are conditionally independent.
So the intuition is a bit difficult. These results, again, are quite new, so we haven't studied them in detail yet. But the algorithm is quite well established. Some of the ideas, I think, come from something known as a Vecchia approximation, which basically says that if you have sort of Markov properties in a certain field, then there are some nuances here that go into it. So the map also has fill-in edges, and depending on the ordering you're choosing. And if your fill-in edges are between cells that are far away on the true graph, then you can often neglect these fill-in edges. And sort of that underlies some of the logic that leads to the super sparse ordering we get here. So in these systems we've tested it so far, this seems to work very well. But unfortunately, I cannot offer more intuition for now.
That's great. I think that's very helpful already. And I see a question from Led Duke, who is asking, this method can be used as a sampling method like MCMC as well?
Theoretically, yes. Practically, I would a little bit advise against it. So it's like a generative modeling. It's not really like MCMC because it doesn't sample sequentially. It's more like generative modeling, where if you have a really good map, you could just generate Gaussian samples and transform them into samples from a joint distribution or from the posterior. In practice, that's generally not a good idea because that only works if your map is really complex enough to capture all the features in your joint space. And for that, you usually need really complicated and expressive maps, something like neural networks. So what we are doing in practice often is we're using something called a composite map, where our Gaussian noise comes from a forward application of this map, and that preserves some of the features the map didn't capture. That gets a bit complicated, but relates to the same reason why the ensemble Kalman filter works so well for non-Gaussian samples sometimes, because it preserves some of the features where a linear map can't capture. So yeah, I wouldn't use it directly for sampling. I would use it to transform prior ensembles, if you have a choice. Yeah.
Thanks, Max. And one more question from Peter Jan. Would Sheffer's algorithm work in high dimensions? If so, it could make localization in most data simulation methods much more efficient.
Yes, it scales really nicely with dimensions. From what we've tried so far. So it's a very, very efficient algorithm. Of course, you need a data assimilation method that can exploit conditional independence very nicely. So for example, my co-author Berent Lunde has recently published a paper on the ensemble information filter that can exploit conditional independence very efficiently. And he's already making use of that. So if you want to learn more about this, feel free to reach out to me or to Berent.
Thank you, Max, very much for the talk. And with that, I'll move to the last speaker of